Hello there, Sam and Andrew from Shielded Labs here with another Crosslink update. Recently, we've been working on testing, and that, of course, means being able to run tests in this manner, where we run offline tests without network connections. These offline tests simulate presenting various data coming from the network to our node, and whether or not and then we test whether or not it accepts and rejects and observe the state. Now these are interesting. They're not unit tests per se. These terms are very complicated, I think, or they mean different things to different people. What we have is there's a file format or a data format, I should say, which we can both pull from disk and generate, and then we feed that data format to the program, which processes these instructions to run the test. We'll take a look at those in a second, but first I just want to say here in this test, if I break it and recompile the test, which because we're using Rust will take a little bit, we're going to see when the test, at what instruction exactly the test failed. In other words, when it deviate from our expectation. And then we'll also show, of course, the visualizer is not in use here, but we can also build with the visualizer, go in and inspect the state of a test. So here, the test failed. So these instructions worked, and then we failed on this one, and then these are the ones that come afterwards. Very useful. So then if we also wanted to run all the tests with the visualizer, we can do so as well. Of course, then we'll have to wait another compile run. Andrew, is there what else is there to say about the instruction format while we wait?
So the instruction format is a binary format. It's fairly simple, but we've chosen that for a few reasons. One is that the data that we're getting off the network is just going to be effectively binary data, and so we need to be able to handle that kind of the canonical form that we're going to get presented in, as well as handle the possibility of malformed data or maliciously presented data.
Right there. I've shown the visualizer running the test now, so now the viewers can now see your screen. So you can actually just show them the format.
Brilliant. Thank you. So as well as just running the actual canonical data, it also means that we can save any arbitrary data easily from disk, which could have been generated from the visualizer, from arbitrary code, or in the test themselves, as I think you showed it just a bit earlier. If we take a look at the format here directly, one other thing about the format itself, or the benefit of the format of itself, is that it, because we're just using bytes, we're isolated from any kind of Rust type changes or Rust member changes that don't directly affect the serialization. So it helps us avoid churn on changes that aren't actually meaningful.
Maybe the best way to say that is if we, for example, change the format of proof of stake blocks, then that changes what we are testing, and so it makes sense that much of the test would have to change. But if the data is the same, because of course all programs just transform data, and so if the data that goes in and comes out is the same, then that's the thing we're testing. We're testing the program end to end without doing network connections that take time, so that the tests can run quickly.
And because we know exactly the sequence that things are going to be happening in, it means we get to avoid any flaky race conditions or other reasons for inconsistent tests. So the format itself is very simple. We have a short header that just identifies this as our test format, says how many instructions we have in our stream, and then where locates them. And then immediately following the header is this big binary blob of data, just kind of completely arbitrary, can be any bytes. And following that are the instructions themselves. And then the instructions say what kind of thing they're doing, whether they're loading proof of work blocks, loading proof of stake blocks, or various other things. And then, if needed, they will reference data in this binary blob to that will actually make up the serialization of this proof of work or proof of stake block. And so we basically just load this in memory, treat this as an array, iterate through it, and run all of our normal operations. There's a kind of separation of concerns where the test data basically gets piped in the same way that the BFT consensus data would normally.
Yes, exactly. We run on the same rails, or code paths, I should say.
So we're testing as much as possible the real code that would actually be running.
Mm. And there's also an additional advantage here, which is having it be bytes. When we write our code, we add types in order to try and know that things are in a consistent state, etc. But the thing we want to test as a program, we're writing a program that is exposed to the internet and any malicious actors. We want to make it easy to construct malicious inputs or malformed inputs, and having just the raw bytes makes that as easy as it could be. All right, I guess, do we have anything else to say?
I think that's it from us for now.
All right.
Yeah.
Well, until next time, stay tuned. Yes.